Hello guys, and thank you for watching this video lecture. Today we're gonna study Python generators. Python generators are considered as powerful tool for creating iterators in a memory efficient and readable way. Unlike regular functions that return a single value and terminate, generators use the yield keyboard to produce a sequence of values lazily. It means they generate each value only when requested. This is especially useful for working with large data sets or infinite sequences because generators do not store all values in memory at once. Generators enable efficient looping and can be paused and resumed. It means they maintain their state between iterations. Generators are commonly implemented using generator function or generator expression, as they play a crucial role in streaming code that requires iteration over potentially large or computationally expensive data streams. So in today's lecture, we're gonna explore Python generators in depth. First, what are the generators? Generators in Python are a type of iterable. They generate values on the fly. So because of this feature, they are memory efficient for handling large data sets, infinite sequences, or data streams. Already we saw this, they store all elements in memory. However, generators produce one value at a time and pause execution until the next value is requested. The generators are defined using functions with the yield keyword or using generator expressions. So there are some key characteristics for the generators. They follow a lazy evaluation mode. It means values are generated only when requested, and in this way, they can reduce memory usage. Generators have a single iteration only. It means generator can be iterated over only once. They are exhausted after a complete iteration. Generators use yield to return something. The yield keyword produces a value and suspend the function's state, and it will be resumed when the next value is requested. When calling a generator function, it returns a generator object, which can be iterated using the next function or in a for loop. Why we use generators? Because they are memory efficient for handling large data sets, infinite sequences, or data streams. Okay, let's try the first one, the simple one. I'm gonna generate one simple generator that yields number from 1 to 3. Okay, so let's try here def number generator, and then here yield 1, right? Yield 2, or for example, yield 3, right? This is our function. This is a generator. Then I can call this function. For example, gen is equal to number generator, then print next, right? If I run this one, I will get 1, right? Then if I copy paste this one here, then I will get number 2. Then if I run it again, then I will get number 3, right? So this number generator function here, this yields one number at a time, and this next gen retrieves the next value from the generator. Also, I can go and try this one for in a for loop. For example, for I in number generator, then print I. Okay, then run it. You can see here 1, 2, 3. This for loop iterates over the generator and it automatically handles stop iteration. Once exhausted, the generator cannot be reused. Next, I'm going to try a generator that yields even numbers up to a specified limit, right? So def even, and in here, I'm going to get one L. This is the limit. N is equal to 0, while N less than L, then yield N and N plus 2. Okay, this is the function, right? Then I can call this function here for I in even, and I pass here 10, right? Then print I. So you can see here 0, 2, 4, 6, 8, right? In this way, I can print the even number. The generator here yields even numbers starting from 0 until this L, until this limit, and each yield pauses the function, and then it will be resumed with the next value when it is requested. And the for loop here iterates over the generator and print each value. The next example, I'm gonna try a generator expression to create square of numbers, right? So this is a generator expression for squares. Squares is equal to x square for x in range of, for example, 10. This is a generator expression. In order to print, I'm gonna just convert these squares into a list and print them, right? You can see here 0, 1, 4, 9, 16, 25, 36, 49, right? This generator expression creates a generator without defining a function. It's memory efficient because values are generated on demand. Next, I'm going to create a new generator and iterate directly. So s squares is equal to x squared for x in range of 10. Then I'm going to use a for loop to print them, right? For I in squares, right? Print I, okay? So run it. No need to have this one. So we can see here 0, 1, 4, 9, and so on. When we use list to print them, this converting to a list with these list squares exhausts the generators. So a new one is created for the for loop here. Next, I'm gonna try a generator that yields Fibonacci numbers up to a specified limit. You know Fibonacci numbers, so the first one is 0, the second one is 1, the third one is the sum of the two previous one, right? So the next one is 1, the next one is 2, 3, 5, 8, etc., right? So def fib, and we get up to L, for example. So A and B equals to 0 and 1 by default. So while A is less than L, then yield A, and then A and B is A is equal to B, then B is equal to A plus B, right? So the function is correct. Now let's try this one. X is equal to, for example, fib 10, and then we will print list X, right? So here we go. You can see here 0, 1, 1, 2, 3, 5, 8. The generator maintains state A and B between yields. Each yield A that we have here produces the current Fibonacci number and then updates A and B. The generator stops when A exceeds this limit. Next, I'm gonna try a generator for an infinite sequence of prime numbers with a way to control output, right? For example, def. So first here, we're gonna define a function to check whether a number is prime or not. Then we're gonna write a function to generate prime numbers. This function yields prime numbers independently. And then is prime, the first function, it's a kind of helper function that checks if a number is prime or not. And then later we use next when we call the function to retrieve the next prime numbers. And in this way, we can have control over how many values to fetch. So the first function that we're gonna try is prime, just to check whether this number is prime or not, right? So we're gonna receive one number, n, and if n is less than 2, then return false, because less than 2 cannot be prime, right? Then for I in range of 2 and integer of n in power of 1 by 2 plus 1, and then if n mod I is 0, return false, otherwise return true, correct? So this is our function, so let's see, it's okay. Next, here, I'm gonna find another function as the prime generator, n is equal to 2, and while true, if this number, the next number that I'm gonna receive, is prime, it means I call this function, then yield n, right? And then go to the next one, right? So let's try this function as well, correct. Next, I'm gonna call this function. So for example, p is equal to prime generator, and for in range of 10, print next p. Okay, so let's see this one. 2, 3, 5, 7, 11, 13. So these are 10 prime numbers. The next example that we're going to try is generator pipeline. It means we're going to try chaining operators to process data in states such as filtering and transforming numbers. So in this example, we're going to get some numbers, right? For example, like 10. Then we generate 10 numbers, and then we will filter only odd numbers, and then we will square them. So we're gonna have three functions. So the first one, def integers, and in here, for example, up to n, then for I in range of 1 and n, yield I, right? This is the first function. The next function is to filter odd numbers, right? So filter underscore odds, and then here n, and for I in n, if I mod 2 is not equal to, because we want to have odd numbers, right? Is not equal to 0, yield I. Okay, then once we filter the odd numbers, we want to square them, right? So def squared, and then here n for I in n, then square them, right? So let's call them, for example, a is equal to squared filter odd number integers, and then we will print least pipeline, right? So let's run them all together. That's correct. Up to 10, then we filter only odd numbers. It means 1, 3, 5, 7, 9. Then we square them, right? 1, 3 square, 9, 5 square, 25, 7 square, 49, and 9 square, 81, right? So these three generators, 1, 2, 3 generators, we chain them together. These integer generate numbers. Or if you want to take out odd numbers, just you make it equal, right? And if you run this one, then you will have the other side, 4, 16, 36, and 64. It means for 2, 4, 6, and 8, right? This is a kind of pipeline. The pipeline processes data lazily, and they generate only the necessary values. The next one, I'm going to use yield from to delegate yielding to another generator. For example, I have def and sub underscore generator, and in here, for example, we have yield A, then yield like B and yield C, right? This is a simple one. Then we have another one. So this is sub generator. The next one, I'm going to call it as main generator, right? And the main generator yield here start, right? To show how it works. Then I'm going to yield from the sub generator from here. It means print this tree, then come back here, right? And end. Okay, so let's call it for I in main generator, then print I. So let's see the output. You can see here, start has been printed here. Then yield from sub generator called ABC here. Then end has been printed here. This yield from sub generator delegates yielding to the sub generator here, and this way we can simplify the code. The main generator yields its own values like start and end, and all values from the sub generator like ABC. This is useful for composing generators or handling nested iterables. The next example is a generator that receives input via send to modify its behavior, right? So def counter, and in here count is equal to 0, count is equal to 0, and while true, receive is equal to yield count. If received is not known, then count is equal to receive. It means we update count with the sent value. Otherwise, count plus 1, right? So gen is equal to counter, then print next gen. Then I'm going to send 5, then print next gen. Then again here, print next gen, right? So let's try. This one first, it's okay. This one, 0, okay. This one, 5. This one, 6. This one, 7, right? The generator yield count and accept a value via received is equal to yield count. Then gen.send5 send 5 to the generator. It means updating the count. Subsequent next that we have here calls increment count from the last value. And in this way, we can see how two-way communication works, and it is useful for dynamic generator behavior. And the last example here is I'm going to write a generator to read a large text file line by line. It means we are not going to load the entire file into the memory. We just go line by line, right? So def read, and we pass the file path, right? Okay, so try and accept. Then with open file path R as file for line in file yield line.strip. If there is a problem here, accept file not found error and yield file has not been found. Now let's call it for I in just read, and I'm going to pass a file like python.txt and then print I. You can see here, we can run it, and you can see the output here. The difference is this generator load line by line, load the file not line by line, not all at the once. The generator reads one line at a time, and in this way, it can minimize the memory usage. This yield line.strip produce each line without the trailing new line. This is ideal for processing large log files or datasets. Okay, that's all for today. Thank you very much for your attention. Generators use significantly less memory compared to lists for large datasets. For example, if a list of 1 million integers might use up to 8 megabytes, but a generator uses constant memory. Generators are slower for small datasets due to the overhead of lazy evaluation. In this case, use lists for small and frequently accessed data. And lastly, generators are versatile and memory efficient tool in Python, and they are ideal for handling large data sets, infinite sequencers, or complex data pipelines. Thank you very much for your attention, and please feel free to send me your questions by leaving a comment below this video. Thank you, and see you in the next lecture.